Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library, and I have a great story to tell you. Please make yourself comfortable and prepare for a new space cruise because we are returning to space tonight. And this time, we are going to travel across the galaxy and beyond. Our travel will explore space oddities, phenomena that defy our imagination or keep a part of mystery, like neutron stars or black holes, or phenomena that are speculative, hypothetical, like dark matter, and types of planets that could exist theoretically, even though they have never been observed or proven, and more planets existing, or possible phenomena. This sounds complicated, but don't worry at all. Even if you are unfamiliar with space and physics, we will advance step by step and in terms that everyone can understand. All you need to do is relax. But first, I would like to let you know that we have a Patreon page for those of you who wish to and can support this project, get more of it, and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3.50 per month, but it doesn't mean you will get less. We let people contribute what they wish or can, and everyone gets everything that is on our page. Because the world is a better place when the sun shines for everyone. You will gain access to 21 exclusive episodes, and we add a new one every month. And you can listen to and download all these episodes with and without background sounds. And as a token of gratitude, we offer advance releases to our patrons. We have added links to Patreon as well as different streaming options, which may be better suited for you. You will find them in the description of the episode. But before we begin, let's take a moment together to prepare for our journey ahead. If you'd like, gently close your eyes and let your daily concerns drift away. Find a position that feels natural and cozy. Perhaps make small adjustments until you're perfectly comfortable. Now draw in a deep, nourishing breath. And as you release it softly, notice how your body responds. Feel the warmth flowing from your neck down through your shoulders, melting away any tension. Let your facial muscles become soft, your jaw loose, your fingers naturally open, and your legs completely at ease. As you settle into this peaceful state, my voice will be your gentle companion as we begin our exploration together. For our first visit, we are going to leave the solar system and travel a few hundred light years, which is pretty close at the scale of the galaxy, to explore a fairly small but incredibly dense object, a neutron star, the closest one ever found. And I will also tell you about pulsars and magnetars. So, what is a neutron star? To understand it, we need to talk about the life cycle of stars. As you know, it is believed, and there is strong evidence for this, that stars appear, live, shine for billions of years, generally, and then they die. They vanish once their internal fuel is spent, when the nuclear fusion reactions that sustain them can no longer continue. At that point, the star does not gradually fade or gently contract into darkness. It dies with glory, and the way it dies depends on its size, its mass, and its composition. A star about the size of the Sun, or a bit less, which is average in comparison with other types of stars, will tend to become a red giant, and what will remain of its core after that is called a white dwarf. But what does it mean? A red giant is what happens when the core of the star runs out of its main fuel, hydrogen, that for hundreds of millions of years it fused into helium. It is not like a switch that would suddenly be turned off. The phenomenon takes time. Hydrogen becomes rare inside the core of the star, but the fusion reaction goes on, including in its upper layers. But the core is where hydrogen goes missing first, and when it happens, the core contracts because of gravity. This contraction makes it heat up. It becomes warmer than it already was, and in turn, this heats up the outer layer of the star. As a result, the star begins to grow, not in mass, but in volume. It occupies more space because the outer layers inflate. And this is not a marginal change. The star becomes gigantic compared with its past size, dozens of times bigger. For example, in the case of the Sun, it is expected to grow so much that it will reach the Earth's orbit when it turns into a red giant. But this is not the end yet, because inside the core of the star that has contracted and heated up, temperature and pressure have become sufficient to start fusing not just hydrogen, but heavier elements, especially helium, the product of hydrogen fusion. So at this stage, helium atoms fuse, merge into oxygen and carbon atoms, and for some time, the star keeps living on its stock of helium until helium also runs out. And at this point, the end is near. There is no fuel left to burn that could keep the star producing energy. If you would like more explanations about that, you will find them in the story about nuclear fusion in my library. The general rule is that fusion of light atoms is exothermic. It makes energy available to be released because the new atoms need less binding energy. The bigger atoms are, the more likely they are to need extra energy to fuse, and so the reaction becomes endothermic. It needs energy available to be consumed to take place. This is why the fusion of heavy atoms cannot be a good fuel for a star, because instead of releasing energy, it consumes some. So, as fusion reactions die down in the core of the star, where carbon and oxygen pile up, the core expands again and cools down, whereas the outer layers of the star dissipate and their matter forms what is called a planetary nebula, a cloud of matter floating in space. The core cools into what is called a white dwarf, a body where fusion reactions no longer take place. It is mainly made of carbon and oxygen, and it is much smaller than the original star. The Sun, for example, could end up having a core about the size of Earth. But a white dwarf is still very massive. Some of its matter has been shed and is now part of the planetary nebula. But a white dwarf produced by a star a bit more massive than the Sun could perfectly end up being as massive as the Sun is while having the size of a planet. This very dense body is called a white dwarf because even though it no longer generates new energy with fusion, it is still intensely hot and it keeps radiating, emitting energy. White dwarfs may still appear as very small stars, little shiny points with a faint light for billions of years, but eventually they should cool down and turn into black dwarfs, the dead core of a star that is now cold and no longer radiates light and heat. I said should, because the transformation of a white dwarf into a black dwarf is estimated to take a very long time. Actually, more than 13 billion years. That is the estimated age of the universe. So at this point, even the very first stars would not have enough time to turn into black dwarfs. And if these estimates are correct, black dwarfs are objects that should start to appear in the future, in billions of years. But there are none yet. So that was the outcome of the death of a star that belongs to the same category as the Sun. It turns into a red giant, loses some of its matter that forms a planetary nebula, and the core remains as a white dwarf. But as you see, the sequence of events in the late stages of the star's life depends on physical reactions that happen inside it. And these reactions depend on the mass of the star, its quantity of matter. What if the star is much bigger than that, 10 or 20 times bigger, more massive than the Sun? A giant star. In this case, the core of the star is also much bigger, and this means that the gravity, the gravitational force, and the heat inside the core are going to be higher, so high that fusion reactions can continue after the disappearance of hydrogen and helium because there is enough energy available. These giant stars go through the same process of exhausting their hydrogen reserves. Then they fuse helium atoms, and turn them into carbon and oxygen. But at this stage, their mass is enough to fuse carbon into heavier elements. Silicon, sulfur, iron. And only once these elements, especially iron, form the core of the star, it can burn no more. With the extinction of fusion reactions comes a collapse. As fusion reactions no longer push outward, the star's core suddenly collapses on itself due to gravity, and it becomes so tightly packed that even subatomic particles like protons and electrons merge. In other terms, the gravitational force is enough to overcome the resistance of atoms. As you know, There is a lot of empty space inside atoms, with a significant distance between the nucleus and the cloud of electrons around it. The sudden disappearance of this empty makes the core shrink dramatically. The star's core, the size of Earth, can shrink to a ball with a radius of just a few miles, and in this core subatomic particles have merged. As you know, a distinction is usually made between three different types of particles inside atoms. There are protons and electrons, which each have opposite electric charges, and neutrons, which have no net electric charge. In reality, protons and neutrons are themselves made of smaller particles, but we don't need to go into that for tonight. The mergers of protons and electrons form only neutrons, and the atomic organization of matter disappears. The core turns into a dense pile of neutrons, where, due to this sudden compression, temperature rises to inconceivable levels, billions of degrees. The outer layers of the star are suddenly pulled into it, which crushes it even further, and the sudden accumulation of energy cannot be contained. So the core explodes, and what happens is called a supernova, an explosion that sends a powerful shock wave in space and disseminates large amounts of matter, of material, into space, especially these heavier atoms like iron and others that have just been produced by fusion reactions, from gold to uranium. It is believed that all these elements that are present around us, including inside our bodies in small quantities, must have appeared and been disseminated by a supernova of this kind billions of years ago, before the formation of the solar system. And when our system formed, it reused some of this matter that had been transformed in the last moment of an extinct star system that disappeared before the solar system began to form. So finally, we are getting there. What remains of a giant star above 8 to 10 times the sun's mass can form a neutron star, which is actually smaller than a white dwarf, but much denser. Inside a white dwarf, gravitation is not enough to break the resistance of atoms, so a white dwarf remains made essentially of carbon and oxygen. The elements remain distinguishable, whereas inside a neutron star, there are no longer distinguishable elements, just a mass of neutrons, because as we saw before, electrons and protons have merged. So typically, a neutron star is 1,000 times smaller than a white dwarf, but with a similar mass and sometimes a bigger mass. Neutron stars are like an intermediary body between white dwarfs and black holes that we will talk about later. If the giant star is not 10 or 20 times more massive than the Sun, but 50 or 100 times or more, the collapse of its core may theoretically create an even denser black hole. It is believed that neutron stars can appear when stars that are at least 8 to 10 times more massive than the Sun and up to about 25 times the Sun's mass end their life cycle. Below 8 times, a white dwarf is more likely, and above 25 times, a black hole. But it is not that systematic, because the mass is not the only factor. The richness of the star in metal can be one too. We will visit a black hole later, but for the moment, let's talk about neutron stars and the different forms they can take. First, white dwarfs are probably much more common than neutron stars. It is estimated that 97% of stars are not big enough to form a neutron star, and only an even smaller fraction are supergiants that can leave a black hole when they die. This state of matter, where there are only neutrons, results from a kind of equilibrium. Pressure, gravitation, is strong enough to compress matter to the state of neutrons, but on the other hand, there are forces that prevent further collapse, forces that protect the integrity of neutrons. These forces are called neutron degeneracy pressure and repulsive nuclear forces. We don't need to go further into these forces. Let's just bear in mind that they resist, they counterbalance gravitation and stop the collapse. But this works up to a point. Theoretically, a neutron star can have up to twice the sun's mass, above about 2 times. That is just an estimate, and it is still discussed between physicists because different forces are at play and their interaction is complex to estimate, but it gives an order of magnitude. So above 2 times, the collapse process could not be stabilized, and further collapse of the core of the body on itself would happen. Further compression would make a black hole appear. The black hole, with still the same mass, but occupying an even smaller space, and in which even neutrons have disappeared. But we will come back to that. Still, even though they are not black holes, neutron stars have a density that is hard to imagine. The mass of a star like the Sun, contained inside a body that is just a few miles across. This means that a little bit of neutron star material contains an extraordinary quantity of matter. To take an example, the bodies of all humanity, all 7 or 8 billion people, compressed like that, could fit into a matchbox, and there would be some space left in the box, because precisely the matchbox of a neutron star material would be estimated to weigh about 3 billion tons. Gravitation at the surface of a neutron star would be around 200 billion times what it is at Earth's surface. This is inconceivable. And another consequence of this enormous mass in a small space is a strong magnetic force, a powerful magnetic field that surrounds the body. These powerful magnetic fields are important because they are organized around 2 poles, like the Earth's magnetic field, but billions of times more powerful. A magnetic axis exists between these 2 poles, and the magnetic field may funnel jets of particles out along the 2 magnetic poles, so a beam of radiation can come out of the pole. And another characteristic of neutron stars is that they rotate very fast on their axis. They rotate fast because the much bigger star they were born from rotated, and when it disappeared, the core kept this rotation, but it is much smaller, so the rotation rate measured at the surface became much higher. In physics terms, there is a conservation of the regular momentum, but you can easily picture it while imagining a figure skater doing a spin. When they are spinning, their rotational speed can accelerate if they draw in their arms. It is not an acceleration due to the additional effort. It is because drawing in the arms decreases the inertia, the moment of inertia, and mechanically it makes them rotate faster. This is what happens on a different scale when the star's core collapses to become a neutron star. The radius suddenly diminishes, but as the angular momentum remains constant, the rotation accelerates. So typically, a neutron star rotates on its axis in a matter of seconds or even milliseconds, extremely fast. Now, when you combine these radiation beams coming out of the magnetic poles and the fast rotation, you get what is called a pulsar, seen from afar like from Earth, or more exactly, observed from Earth with instruments, because pulsars are not visible to the naked eye, and instruments are necessary to detect their beams of radiation. So, seen from afar, a pulsar is like a lighthouse that would rotate very fast. Each time the beam points at the observer, a signal is perceptible, and this signal repeats very regularly. It follows a neutron star's rotation. Pulsar means pulsating radio source, and thanks to this signal that they repeat very regularly, thousands of them have been identified in our galaxy alone. This is only a fraction of existing pulsars, probably, given the number of dead stars in our galaxy. I mentioned earlier that the majority of stars are not massive enough to leave a neutron star behind, but there are billions and billions of stars in our galaxy, so that still leaves hundreds of millions that are big enough to turn into a neutron star and become a pulsar. A particularly and less frequent type of neutron star is called a magnetar because they have an extremely powerful magnetic field. They are not necessarily bigger than other neutron stars. As we saw, their mass cannot exceed 2 solar masses, otherwise they collapse further. But their magnetic field is particularly powerful, and they tend to rotate slower than pulsars, typically 1 every 2 to 10 seconds. Magnetars have been identified separately from pulsars because they are responsible for bursts of rays that were detected from different parts of our galaxy, and they became the best explanation for that phenomenon. As of 2025, according to the most recent astronomical survey and publications, approximately 30 magnetars have been located in the Milky Way. Not many in comparison with the thousands of pulsars, but this is because magnetars have a short lifespan. Their magnetic field decays quickly, in a few thousand years, and so they become less active and detectable. So there are probably millions of inactive or less active magnetars in the galaxy, and only the youngest have been spotted, the ones that produce spectacular bursts of rays. At this point, we have seen what happens to stars the size of the Sun, a bit less, or up to 7 or 8 times the Sun's mass. What happens to giant stars, the ones that tend to turn into neutron stars, up to about 25 solar masses? But what about supergiant stars that are more than 25 times bigger than the Sun? In their case, the collapse of the core on itself does not end in a pile of neutrons. The neutrons themselves are crushed and cease to exist as such. They form a body whose gravity is so strong that nothing, including the fastest particles or rays in the universe, can escape it if they come close enough. Very dense objects like neutron stars may have a very strong gravity, but this is not enough to capture light, for example. To understand it, we need to talk about the concept of escape velocity. When we are on Earth and we throw something up into the sky, it falls back a little bit because there is friction in the air. This may slow the object down as it rises, but if it falls back, it is because the gravitational pull of the planet attracts it back to the ground. The more energy, the more velocity what we throw has, the higher it can go before falling down. A basketball thrown by hand will rise a few meters. The bullet from a gun can go higher. But this is still not enough to escape the planet's gravity. To escape it, you need to either provide more thrust as the object rises, for example, a rocket. When a rocket traveling to space takes off, additional push is provided for several minutes as it burns its fuel reserves, and this is how it can free itself from the Earth's gravitation. Or you need to give the object enough push, enough initial speed, that the planet's gravity will not be sufficient to stop it from escaping. This is the concept of escape velocity, the minimum speed necessary to break free from the gravitation of an object with a mass. It depends directly on the object's mass and the distance of your starting point from the center of this mass. For example, the escape velocity from Earth's surface is about 25,000 miles per hour. That's 40,000 kilometers per hour. Man-made ships do not reach this speed, and rockets manage to escape despite lower speeds only because they have a continuous thrust during their ascension. Bodies or particles in space don't have that self-propulsion. They receive some kinetic energy that they don't lose as long as they don't collide, but they don't accelerate by themselves. So the more massive the body you try to escape is, the faster you need to go. And this concept was understood long ago in the 18th century with the elaboration of the theory of gravitation. And soon, this theoretical development led to a theoretical question. what if an object was so massive, with such a strong gravitational pull, that its escape velocity was higher than the speed of light itself? The speed of light being the highest conceivable speed, at least based on our current understanding of physics. Then, in that case, nothing, not even light, could escape such a body. This is the concept of a black hole, a body so massive, which doesn't mean so large. Matter is so compressed inside of it that a black hole does not need to occupy a lot of space. But a body so massive that once something has been captured by its gravitation, no escape is possible, or at least, conceptually, no escape without self-propulsion. This is why they are called black holes. Black because not even light can escape them, and you can literally fall into them. But the term hole can be a bit misleading because they are very, very dense, the opposite of a void. For an astronomical black hole to form, a mass of at least 2.5 to 3 times the sun's mass is necessary. Below that, the mass is not enough for the core of a star to keep collapsing on itself. But if 3 solar masses are the lower limit, you may wonder why there are stars that are dozens of times more massive than the sun, and yet they don't turn into black holes. This is because as they burn their fuel during their life, other forces compensate for gravitation and prevent the star's core from shrinking. It is when these reactions die down that what is left of a star, the core, can finally collapse on itself and, if it is massive enough, turn into a black hole. Black holes are sometimes pictured as irresistible vortexes that will swallow anything. This is true if you come too close to them, but their gravitation, their impact on other bodies, is not more powerful than other objects of a similar mass. A black hole with 5 solar masses has the same gravitational pull as a star with 5 solar masses, and there are plenty of them. So black holes can have satellites. They can capture other bodies with their gravitation, but it doesn't mean they will end up swallowing them if these bodies are far enough and have their own speed. If this is the case, the captured body will keep its distance with the black hole. It will stay on an orbit around it. The limit, the point of no return of a black hole, is called the event horizon. Beyond that frontier, beyond that limit, there is no escape left. But as long as it is not passed, a high enough velocity will allow fast particles to escape, like light. This is why visually, the event horizon would be like the limit, the boundary of a black hole. Everything beyond it is dark because light cannot escape. I will leave the physics of what happens inside the black hole for another time. This topic is complicated and still discussed between physicists, in particular because it is believed that at the center of each black hole there is what is called a singularity, a point where gravitation becomes infinite, and there is no theory at this point that can model or describe this phenomenon. But if we keep an external look, a lot of discoveries of black holes have taken place in the past few decades, and two main groups are identified. There are stellar mass black holes, the ones that form when large star cores collapse under their own weight. And there are supermassive black holes, the ones that are believed to be at the center of galaxies and have much higher masses, billions of times the sun's mass. The origins of supermassive black holes is poorly known, but what is likely is that black holes can grow. They can absorb more matter, capturing objects. They can merge, including supermassive black holes, when galaxies collide. And as you may have seen, the first pictures of black holes were released. What we see on them is obviously a black spot, but it is contoured by light. And this sounds paradoxical. I just told you that black holes do not let light escape by definition. So why would there be a visible ring around them? What we actually see, and this is an illustration of Einstein's theory of relativity, is an effect of the black hole on its environment. The definition of gravitation, according to Einstein's theory, is that massive objects affect others because they curve. They warp the space-time, the fabric of the universe. The bigger the mass, the stronger the warping, the curvature. And this curvature does not only affect objects, which also have a mass, as Newton's initial theory supposed. It affects everything, including light, which is without mass. The ring of light that we see on these pictures is not emitted by the black hole. It would come from the effect of the black hole on its surroundings, where space-time is warped, and this affects the path of visible light, allowing us to see something. There would be much more to say about black holes, but we have more things to see on our cruise, and space oddities are not limited to what stars turn into when they die. We have seen that black holes could be extremely massive objects, and as such, contain a big chunk of the matter that exists in the universe, maybe the majority of it. Or do they? Let's talk about dark matter, a hypothetical form of matter whose existence has never been directly proven, but that could represent around 85% of the matter in the universe, if it exists. What is this? And why is this hypothesis so seriously considered? To understand it, we need to go back to the 20th century, when astrophysics and observation of faraway galaxies made giant leaps forward. At the time, the theories of gravitation and Einstein's theory of relativity were already well known and accepted as valid by the scientific community. But a number of observations did not really fit them. In particular, the observation of galaxies and how they moved in space, the observation of their motion. It was observed that galaxies could travel away from each other, and this was an important step in realizing that the universe was in constant expansion. Galaxies also are big masses that interact with each other via gravitation, even though they can be far apart. But the mapping of the universe, at least what we can see of it, soon revealed that something was off. Many galaxies did not behave as they should have based on their estimated mass and the laws of gravitation. But the laws of gravitation could not be thrown away easily. They work, and their predictions have permitted many discoveries, including planets that were guessed before they were observed. So if gravitation was not the problem here, it had to be the mass of these galaxies that was not correctly estimated, and sometimes widely so. Some galaxies should have been more than 10 times more massive than they seem to be to explain their influence, their interactions. This was the unexplained mystery that gave birth to the hypothesis of dark matter. Dark because it is undetectable as of today, not only visually, but also because it seems to not interact with the electromagnetic field, which means it does not absorb, reflect, or emit any radiation. And so, it could be of a different nature than the matter we know of. Its only shared property with familiar matter would be that it has mass. That is why dark matter is speculative. It is detected from our inability to explain observed phenomena. The motion of galaxies is not the only clue that points to its existence. There are other lines of evidence, such as the formation and evolution of galaxies, or the measurement of what is called the cosmic microwave background, a radiation that is a remnant of an early stage of the universe. That makes a lot of unexplained phenomena that could be explained by the existence of dark matter. The problem is that no one has ever observed it, assuming it exists. All about it is hypothetical. Its only interaction with known matter would be through gravity, but we have no idea of its possible nature. Are these gigantic but undetectable masses? Or a few particles with enormous gravitational force? Or something we have not managed to conceive? The primary candidate today would be a kind of unknown subatomic particle, unknown as of yet. The strength of this hypothesis is not just because the existence of dark matter would avoid having to throw away the gravitation theory, which would be very uncomfortable. It is also that its existence can be deduced from various independent approaches, as I mentioned before. Solving the problem raised by one of these approaches with a different explanation than dark matter would be a thing, but solving all of them looks very difficult. And for that reason, even though it is observed, elusive, and at the same time would be expected to make the bulk of matter in the universe, this hypothesis is still the one favored by the scientific mainstream. That's an ongoing mystery, and it is humbling. If dark matter is real, it means that at this point, we barely know about 15% of the matter in the universe, and the rest escapes our perception so far. But if dark matter does not exist, the implications are even more troubling. It would mean that large parts of physics break down, leaving us unable to explain many observations that have been repeated countless times and appear remarkably strong. Until now, on our cruise, we have been looking at large-scale objects or phenomena, but on a smaller scale, at the scale of planets, there could also be bodies that can theoretically exist and would challenge our knowledge of planets, our knowledge of planets being primarily based on the observation of the solar system. We have two big types of planets in our system. There are rocky or telluric planets with a metallic core. It is believed, because heavier elements tend to migrate to the core in their formation process, and around this metallic core, they have a rocky envelope where the dominating elements are silicon, oxygen, hydrogen, and to a lesser extent, plenty of other elements in smaller quantities. And then there are giants, planets with probably a metallic core too, but around it layers of gas. And these ones are divided into gas giants when they are mainly made of hydrogen and helium, like Jupiter or Saturn, and ice giants when they contain more astronomical ices, like water or ammonia, like Uranus and Neptune. But the solar system is just one system among billions, and nothing says that other types of planets do not exist. Planets with a different structure or a different composition. This is all speculative, but theoretically possible. And now we are going to review different types of planets that may or may not exist somewhere in the universe. Like coreless planets, carbon planets, planets covered by oceans or orbiting around a black hole. The concept of a coreless planet is not a hollow planet. Hollow planets were imagined in different contexts, including in fiction, along history, but not given what we know about the universe. It looks impossible for a hollow planet with just a shell to form. There is no reason for a void to exist inside, at least not naturally. A coreless planet would be a rocky planet without a metallic core, a terrestrial planet that would just be a giant rocky mantle. The formation models take into account the type of material available when planets form around the star, and there is a lot of metal in this material, especially iron, as we saw before when I told you about the appearance of new, heavier atoms in large stars when they reached their last moments. Iron is a frequent outcome of fusion reactions, and for that reason, it is relatively abundant. So a rocky planet without a lot of metal and a metallic core is hard to conceive. If we look at the solar system, we even have an example of almost the opposite with the case of Mercury, which has a big metallic core, proportionally, and a small rocky mantle. But the formation of a planet made primarily or mostly of rocky material is not unthinkable. It would theoretically be possible in cooler regions of a system, far from the star. A first mechanism would be when the planet accretes far from the star, in a cooler environment. Accretion means the progressive absorption of material on its orbit by gravity. In that case, it would happen in an environment where metallic iron is bound into silicate material crystals. In other words, iron would be trapped into rock structures that would not melt and would not let it escape. In that case, the formation mechanism would not allow metal and rock to be separated and the planet to differentiate. That is to say, to have a core and a mantle with different compositions. Another possibility would be that the planet accretes from water-rich and iron-rich material, also slowly enough and far enough from the star for water and iron to react and form iron oxide, rust, before differentiation of a metal core has taken place. In that case, provided iron droplets are mixed enough with other elements, iron could stay entirely trapped in the mantle and no core could form. Maybe we have already detected coreless exoplanets and we don't know it, because apart from their internal structure, their sizes are expected to be similar to planets with a core. They would form far from the star based on models, but this does not exclude the possibility of a migration within a system, so they could move to a closer orbit later. The opposite to a coreless planet would be an iron planet, a type of planet with a metal core and little to no mantle. Mercury is almost one, and that is proof enough that metal planets, or almost metal-only planets, are a possibility. The formation process here could be different. These planets are expected to form near the star, because this is where the concentration of iron-rich material would be found when a new star system appears. They could form naturally with mostly metal, but, like it is hypothesized for Mercury, they could appear after collisions. A regular terrestrial planet would form, and later, large collisions with asteroids would strip it of its mantle that would be ejected into space and lost. So the iron planet in that case would be the remaining core of a rocky planet that has been exposed and has cooled down. A consequence of being a metal planet is that there would be no plate tectonics or volcanism, just different layers of metal, with a colder, solid outer layer and a hotter core where metal is melted. Yet another type of theoretical planet with a different composition would be a carbon planet. Not a planet made only of carbon, but one where there would be more carbon than oxygen. What does it mean? Rocky planets in the solar system, like Earth, Venus, Mars, formed in an environment where there was more oxygen than carbon, almost twice more. Their carbon to oxygen ratio is around 0.55. It means that in terms of mass, Earth, for example, has a bit more than 2 pounds or 2 kilograms of oxygen for 1 pound or kilogram of carbon. What we call rock are compounds made mainly of silicon and oxygen, silicates. This seems to be the norm because oxygen is more abundant than carbon in the universe. Oxygen is the third most prevalent element after hydrogen and helium, whereas carbon comes in fourth. But we also know that all star systems don't have the exact same carbon to oxygen ratio. Some are richer in carbon than ours. For example, exoplanets have been detected with a higher carbon-oxygen ratio, as high as 0.78, and so there could be planets which would look like Earth in terms of size and internal structure, but the domination of carbon over oxygen, or the parity, would mean chemistry and climate at their surface would be very different. The equivalent of geologic features on Earth may be present, but with different compositions. For example, instead of being composed of liquid water, the rivers might consist of oils. If the temperature is low enough, gases in the atmosphere may synthesize into hydrocarbons that could rain onto the surface, and the surface would be expected to look dark and reddish from hydrocarbon deposits. Yet another type of planet, not because of its composition, but the object it orbits, would be so-called Blanets, with a B like black. Planets that orbit a black hole. This is more than purely theoretical. It is likely to exist, even though none has been detected yet. Blanets would be fundamentally similar to planets that could be of a different kind, and they could be located around supermassive black holes. It is a bit more difficult to imagine them around a black hole born from the collapse of a big star, because even though this supergiant star probably had planets, it went through a supernova that destroyed the system or expelled its planets. It is not completely impossible, though, because planets could be captured later, once the black hole exists. We know that there are rogue planets that escaped the system when they formed, and some of these rogue planets may even travel between galaxies. But a supermassive black hole at the center of a galaxy is a better candidate, because it could capture many of these planets, and even more because there is an accretion disk around such a black hole, a region with enough material in orbit to form new bodies, possibly thousands. There is a safe zone around such black holes where satellites can exist, a zone where they are close enough to be captured by the black hole's gravitation, but far enough for an equilibrium to form between their speed and the black hole's pull, so they can adopt and stay on an orbit. These are different types of terrestrial planets that could be markedly different from the ones we know. But gas giants could also be different. The ones we have in the solar system are quite distant from the Sun, but we know that there are giant gas planets that orbit closer to their star. This is what is called a hot Jupiter, hot because of the proximity to the star. And when this happens, they could become something called Chthonian planets, gas giants that would have been stripped of their gas layers by the star, leaving only their solid core that would look a lot like a terrestrial planet. Or there could be helium planets. On Jupiter and Saturn, hydrogen is the main component, and helium is the secondary one. A helium planet would be one where helium dominates, and they might form in a variety of ways. The first possibility is hydrogen evaporation. If a planet orbits close to its star, stellar radiation can strip away lighter gases more efficiently, and hydrogen, being lighter than helium, is lost first. So over time, hydrogen could be depleted and leave helium as the primary component of the planet. Another type of planetary object with a layer of helium rather than a planet could be from a small white dwarf. You remember what white dwarfs are? We spoke about them at the beginning. They are the remnants of sun-sized stars after they turned into red giants when they exhaust their hydrogen reserves. Now, in a binary system, a system with two stars, where both have passed their main sequence and died, turning into white dwarfs, one may have lost so much of its mass that it approaches planetary mass, and it orbits around the larger white dwarf. The planetary nebula left by the stars would be rich in helium, and this smaller white dwarf may be surrounded by layers of gas dominated by helium, making it look like a gas planet, even though technically it used to be a star before, which is why it would be called a planetary object rather than a planet. We are approaching the end of our cruise, and it is time now to return to Earth after this little exploration journey. As you see, space is still full of wonders and unsolved mysteries and phenomena that wait to be discovered or understood. You will find other space exploration journeys in my library to the solar system, galaxies, exoplanets, or to similar but not less interesting objects like asteroids and comets. For now, you can close your eyes and let yourself go to sleep. And until we meet again, good night. Sleep well.